Anybody know where this is? It's the Hoover Dam. Yeah. The Hoover Dam looks differently now. You see how they're building a road here? Now you don't drive on the dam anymore. Now there's a bypass where you can drive over a bridge in front of the dam. Yeah. All right. So homework number 1 is due on Wednesday the 22nd, and like I mentioned, that's not yet posted on Blackboard, but I'll get it on there tomorrow. And what we're going to talk about today is we're going to continue our discussion we left off back in December, early December, talking about flow resistance. Water moving through pipes loses pressure as it goes through the pipe because of energy losses having to do with pipe friction. So I kept back in fluid mechanics telling you, next semester we'll get into the real details of how to account for that frictional loss. So we're going to finally get into it over the next couple of days. I've already given you the syllabus and the schedule. If you have any questions about that, feel free to stop by during my office hours or send me an email. And I'll send you a message when I have the notes posted online so that you can print those out if you'd like to have them with you. We're in chapter 7 of the book. The first part of the textbook is some fluid mechanics fundamentals, and so we go right into the intermediate material here in chapter 7. I'd encourage you to look over after each class the chapters that I've indicated in the announcement slide. So I'll tell you both the chapter and the subsection that corresponds to each day's class meeting. Just as a matter of general interest and introduction to the course, I like to show this picture of a bridge in Germany. And it's more interesting than a normal bridge because it has water flowing over the top rather than cars or foot traffic. And the genesis for this water bridge in Germany is that there were 2 industrial communities that were separated by a river. And so many years ago, they created a canal from one town into the Elbe River, and to get to this other town, they'd have to go down the Elbe and then up some side canal, and it was indirect. It was a lengthy transit, made even more lengthy by a couple of locks that had to lift and lower the barge between the two towns. And so they thought, well, the way to save time, Germans being efficient, of course, is to connect these two with a more direct route. The only problem is that you can't have a canal going downhill and then uphill, not without having that same problem of a lot of intermediate locks and dams in between. What they realized was that these 2 towns were at approximately the same elevation, and so instead of lifting and lowering the boats each time, if they built an elevated kind of an embankment on either side, as the ground got lower and lower adjacent to the river and then went back up again, they could keep the water lifted, and then the boats would be able to go over the elevation of the river underneath. So it's kind of a cool application, I think, a nice way to spend $500 million. Now, this semester in hydraulic engineering, we're going to consider the amount of water, its timing, and distribution, because hydraulic engineers are sizing the infrastructure that delivers water from place to place. So that can be inside your home, or on a grander scale, it can be the water that flows through a hydropower plant and generates electricity. And we divide the course into 2 main parts. There's the first part of the course where we're talking about closed conduit flow, meaning flow through pipes, where the water is full inside of a container. And then the second part of the course is open channel flow. And so open channel flow would be flow in a river or a stream, or flow in pipes where the water isn't all the way to the top of the pipe. So an example of open channel flow would be in a sewer or a storm sewer. Since that's not under pressure, the water behaves differently than it does when the pipes are pressurized. Finally, we're going to spend a little bit of time talking about reservoirs and how they're sized specifically. We won't talk about the forces so much as the required size that's needed to meet varying demands over time. Now, there's a lot of really interesting side concerns whenever it comes to water. There are legal implications having to do with how much water people are allowed to use. There are economic implications having to do with balancing, number one, like the cost of the materials that are used to convey the water. You know, pipes are expensive. Metal pipes, plastic, concrete, those materials are expensive. And so one of the things that hydraulic engineers always try and do is balance out the cost of making the pipe bigger with the value of less head loss as the water flows through a pipe. If you're sending water from here to there, if you have a really small pipe, the water won't have as much pressure when it gets to there. So you have to figure out what are the requirements at the point of delivery. You know, where you're going to be withdrawing the water, do you need the pressure to be 250 kilopascals? Does it need to be 500? And how much water are they going to be using there? And so there's economic consequences having to do with optimization. And that's one of the cool things about our design project, is that what you'll do is you'll very easily design a network that does the job, that delivers the quantity of water and the pressure that's needed. But then what you'll start doing is you'll start chipping away at optimization, where in this pipe network you'll be making one pipe a little smaller and then another one a little smaller, and you'll just keep pushing it more and more and more until maybe the system starts to fail, where the pressure's too low, where you've gone too far and made the pipes too small. So you'll be balancing out performance with cost. And so hydraulic engineering is a really great way to study that, what's sometimes called parametric optimization or iterative design, and the economic consequences that come from it as well. This is a photo of a pipe gallery in a drinking water treatment plant. And I took this picture when I was in graduate school. This is a drinking water treatment plant in Indiana. And you can see all of these pipes going in every which way. It's very complicated, and we won't design or analyze anything quite as complicated as this, but if you do end up in hydraulic design, there are some pretty nice computerized tools that make it easier to figure out the effect of pumps on pressure, and you'll notice that here are two pumps side by side. Through the semester we'll look at how pumps behave when they have another one that's acting in series versus in parallel, and then the idea of analogous pumps, which is pumps that have similar performance characteristics but are a different size. So that's what we'll spend part of our closed conduit flow doing, is sizing and evaluation of pumps. In the second half of the course, once we're done with closed conduit flow, we're going to look at flow through open channels. This is a picture that I took in the United Arab Emirates a long time ago when I first moved there back in 2005. Where were you in 2005?
Starting kindergarten.
Kindergarten? Yeah? All right, well, that was, I took this when some of you were in high school. This was my first year teaching at the university over in the UAE. And so you'll notice that this is really mountainous. And when it rains in the UAE, because it's so rocky, the water doesn't penetrate down into the soil very much. And it's so steep that the water comes very quickly to the point of discharge. And so they have to have a pretty good read on how large this channel should be, or else the homes that are nearby will become flooded. So this channel just flows right out to the sea. It discharges into the ocean. And the question in the open channel part of the course is, how wide would a trapezoidal channel need to be for a certain flow rate that we're going to be sending through that channel? Jeffrey?
So all this is going to be about estimations and predictions, correct?
No, it's not all estimation. It can be direct measurement of flow rates, and then we could be sizing pipes on like known quantities. Here is a engineered reservoir. This is in Northern California, You know, it used to be a canyon and now it's a lake. The depth of the water varies from year to year, but this is part of the series of lakes and reservoirs in Northern California that makes the Central Valley such a productive agricultural region. And a lot of the vegetables that we eat in this country come from the Central Valley of California. And so part of what we do as engineers makes possible variety in nutrition, variety in the foods that are available across the entire country. And so there's a lot of really interesting kind of like side benefits to providing these big civil infrastructure projects. This is the map that I edit a little bit from year to year, but it's the basis of your design project that I've already kind of given you a sneak peek of. The idea being that here we have a contour map of different elevations, and so you can see in this map you've got the high part of town and the low part of town. This is relatively steep. You can tell that because the contours are close together, whereas this part of town is relatively less steep. But in that design project, what you're going to be doing is based on estimations of how much water people would be using in different parts of the city, and so how much water is going to be coming out of the network at these green arrows. You're going to figure out how big the pipes should be between the junctions. And so you'll use either water gems or some other design tool in order to size the pipes and to optimize and iterate and make it better and more efficient until it's the minimum cost that still satisfies the objectives. So that's kind of the application that we're going to be building towards through the entire semester. And it's a good illustration of what a hydraulic engineer does. The hydraulic engineer is going through a design process to try and just barely meet the objectives, because if you over-deliver, then that just means you spent too much. You know, as long as you have design criteria that are adequate for the needs, like if you know with good confidence how much water is required at M, and you know what pressure is required at M, if the pipe is any bigger than is required to satisfy those needs, then you've wasted money. And the people who pay for this are your clients and the taxpayers, and so a hydraulic engineer is always looking to optimize. So that's kind of the overview of the course and where we're headed. Before we get to any of that complicated stuff, though, we need to revisit the idea of flow resistance. This is a cross-sectional representation of a pipe. And what it kind of illustrates is the turbulence as the water is flowing through a pipe, and the fact that maybe velocities are higher at the center of the pipe where there's less resistance to flow. The velocities are lower at the edge of the pipe where the influence of pipe friction is observed more directly. Here's also a visual representation of turbulence, and you can tell from the colors how much turbulence there is, and this is a computational fluid dynamics model. It was generated by a computer where the computer has divided up this area into a mesh and has an idea of the slope of the channel and what the channel has at the bottom, like the materials that are underneath. And the factors that affect flow resistance include the fluid viscosity. And so we started last semester by talking about fluid properties like viscosity. And viscosity is the resistance to movement. And for most of the semester, we'll just be working with water. We won't have exotic fluids anymore like mercury or glycerin. I mean, hydraulic design is water, but the viscosity of water changes as a function of temperature. And so you'll need to pay close attention to, in some cases, the water temperature will change depending on where it's coming from and where the pipes are located. But that doesn't change a lot. Fluid viscosity varies a little within a narrow band, but what does change a lot are the flow conditions, like the velocity that's going through the pipe and the depth of flow, whether a conduit is uniform or whether it has a lot of change in directions. And we'll look at a diagram, the Moody diagram that we saw last semester in just a minute, because the Moody diagram helps to take the flow conditions into account as it estimates the amount of flow resistance. And so any method we use to try and characterize how much resistance there is to flow should take all of these factors into account. And so remember that in fluid mechanics, when we were doing the experiment having to do with the Hazen-Williams equation, one of the reasons why Hazen-Williams equation didn't give us maximum accuracy is it didn't take a lot of these factors into account. Now, the Hazen-Williams equation is calibrated for just a certain temperature of water, but if you have water outside of that initial calibration, then there's no adjustment for viscosity. The Darcy-Weisbach equation, by contrast, does take all of these factors into account, including whether the flow conditions are laminar or turbulent. Does anybody remember the formula for the Reynolds number? Remember, Reynolds number is unitless, so whatever the formula is, the units should cancel out. Christmas break was wrong. It's the velocity of flow times the diameter of the pipe divided by the kinematic viscosity. Okay? So, if the flow is laminar, it's actually pretty easy to estimate flow resistance. But the flow isn't laminar very often. We had to go to some pretty extreme lengths in the lab to visualize laminar flow. We had to have that really narrow tube, and the flow was controlled with the valve. We barely had the valve open when we were injecting the dye. It's pretty uncommon to have laminar flow conditions, and so normally there's going to be turbulent flow, and that makes it more difficult to estimate the flow resistance because the water is behaving more unpredictably. Now, first, the easy thing. If you have laminar flow conditions, what this diagram and the formula that accompanies shows is that you can estimate the F value, that's the Darcy-Weisbach friction factor, just it's 64 divided by the Reynolds number. So that's a really easy formula, but the problem is that flow is hardly ever laminar. So you won't really ever calculate the F value with this formula. Now, I hope that the Darcy-Weisbach equation, if you don't remember it, at least it looks kind of familiar. This Darcy-Weisbach equation is the formula that we use in the energy equation in order to account for the effect of pipe friction. So remember, the energy equation was the pressure head plus the elevation head plus the velocity head, and then we add the energy that's added by the pump, and then it is P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus the energy that's removed by the turbine, the local losses, and the pipe friction. Okay, so this H sub F formula here, the Darcy-Weisbach equation, is estimating how much energy is lost as the water goes from 1 to 2, how much energy is lost due to pipe friction. If the water's flowing through a channel from 1 towards 2, we know that the pressure is going down. Kind of by definition, it has to be. Otherwise, the water wouldn't be flowing from 1 towards 2. So the pressure is going down, and if we can estimate the H sub F, that'll tell us the rate of pressure loss. So you could, if you had some known pressure at 1, you could predict the pressure at 2 after calculating how much energy was lost due to pipe friction. So here L would be the length of the pipe between 2 points. So L would be this distance. The V in this equation is the velocity inside of the pipe. The D is the diameter of the pipe. Of course, G is the gravitational constant, but F is some friction factor that usually won't be this easy to calculate. But there are a couple of ways that we can determine the friction factor F. One is with the Moody diagram. In class on Wednesday, we'll learn some equations for estimating F, because it's not always convenient to use the paper diagram. Sometimes we want to automate our calculations of F, and so a formula is needed. You can't put this into a spreadsheet and have it look up F automatically. This requires kind of a user interaction that sometimes is inconvenient. But just to get the practice with it, we're going to go through the process of using the Moody diagram to get F. So what we want out of this diagram is on the left vertical axis. So the process that you're going to go through is, first, you're going to consider what's the relative roughness. And so that's the vertical axis on the right side of the diagram. So K sub s, sometimes also assigned to the variable epsilon, that is the equivalent sand roughness of whatever the material is. So if the material is cast iron versus ductile iron versus galvanized steel, you can look up that material property in a table. And then D is the pipe diameter. That'll usually be given in a problem statement. And so you'll have some K sub s to D ratio, and then you use that to start following either on a curve or using a point between the curves as a guide to know what is the intercept with the Reynolds number. And so the Reynolds number is on the board there, excuse me, the formula for it anyway. You're going to need to calculate the Reynolds number from the flow rate and the diameter and the viscosity that's described. So let's actually go through that process now. We have an example here that says water is flowing at 30 meters per minute through a 0.25 meter diameter pipe, and the K sub s value, meaning the roughness, is 0.26 millimeters. We want to know what is the F that would be applying. If we were going to use Darcy-Weisbach to predict the head loss downstream, what F value should we utilize? All right, so first of all, calculate the relative roughness, the K sub s to D of that. All right, so the K sub s to D K sub s to D ratio is 0.26 millimeters. And now we want the units to be consistent. The problem said 0.25 meters is the diameter. So we need to have 250 millimeters in the denominator here for the units to be consistent. And so that ratio is 0.00104. What that means is that we're going to be, here's 0.001, and it's not as far as 0.002, it's like 40% of the way there. Oh, no, I'm sorry, 0.104. So it's barely over the line. So it's not even to 0.00, it's not even to 0.0011. So, okay, just barely above this line. Now what we're going to look for is where should we intersect the Reynolds number. All right, so the velocity that it's describing here of 30 meters per minute, the velocity is going to be 30 meters per minute, and we need to divide that by 1 minute, excuse me, multiply by 1 minute in being 60 seconds. Okay, so that's 0.5 meters per second. We want the units to have a time component in seconds, because the viscosity that we have, and for water, the typical water viscosity in kinematic terms is 1 times 10 to the minus 6 meters squared per second. All right. So will you put that into your calculator and tell me what is the Reynolds number for the water that's going through this conduit? It being the first day of class, did you bring a calculator? No. That's a demerit for you.
Or 125,000.
All right, so it is 0.5 times diameter, which is 0.25, divided by 1 times 10 to the minus 6. So that 1.25 times 10 to the 5th. Okay, so here on our Reynolds number, logarithmic scale. So here's 1 times 10 to the 5th. 1.25 times 10 to the 5th is this way. I'm going to have to disable that. That's kind of annoying. All right, so 1.25. Now this is 1.5 times 10 to the 5th. So it's maybe midpoint between here and here. So we go up from that point, and we want to intersect the curve that we already identified. And so the curve of let's see, what was our relative roughness? 0.001. Okay, so where does this intersect that? So you see how this is going up? So the point of intersection, oh, that's convenient. That's right on this line. So it makes it easy for us to go over to the left, and it's 0.022. All right? Man, I love it when it works out like that. Okay, so the F value 0.022. And just so this gets recorded into the video, let me bring that Moody diagram calculations up on the screen in case you want to refer to it later. So here's our velocity, Reynolds number, and then from the curve we want to follow the 0.001 line wherever it leads to the intersection. So going up from here, going up until we hit that curve. So if it had been 0.0015, so that's between these two, then what you do is you just stay between those two curves until we intersect it, and then we'd go over. Does the Moody diagram make sense to everybody? Good. All right. We are out of time. You know, I've taught this class 75-minute lectures for like the last 8 years. So I'm going to do my best not to keep you over, but once in a while I'm going to misestimate how much we can get through in a day. So when we get together in class on Wednesday, we'll start here on this slide. So just as a reminder, what do you need to be doing so far? Well, get the book if you haven't already. And then I'll email you both when the assignment's ready to go and when the notes are online. Not that I expect you to necessarily start on the assignment tomorrow. It's not due till next Wednesday, but I know some of you are early birds, so I'll give you the advance notice when it's ready. All right, have a good one.